Okay, greetings and welcome everyone to this week's webinar talk sponsored by the Chicago DOE Alliance Center, headquartered here at the University of Illinois at Chicago. I hope everyone is safe and healthy. We're pleased to have another talk from one of our colleagues in Europe today, Natalia Dubrovinskaia, the University Professor for Materials Physics and Technology at Extreme Conditions at the University of Bayreuth, Germany. She's also a guest professor for Advanced Functional Materials at Linköping University in Sweden. Natalia received her PhD and master's from Moscow State University, did postdoctoral work at Uppsala University before moving to Bayreuth in 2001. She has a number of honors, including the Grigory Aminoff Prize of the Royal Swedish Academy of Sciences and a Heisenberg Professorship. And over the years, the past 2 decades, in fact, she and her husband Leonid have built an impressive high pressure program at Bayreuth. And so we're especially pleased that you're here to tell us about chemistry at very high pressure revealed by single crystal X-ray diffraction. Welcome.
Good afternoon, everybody, or good evening. It's 8 p.m. actually in Germany now. I'm still not very comfortable because I don't see myself, but now hopefully it will work. Russell, thank you very much indeed for your kind introduction and for inviting me to give this talk. And this talk is co-authored by Leonid Dubrovinskaia, and I will be talking about chemistry at very high pressures. I saw that Leonid also joined the meeting, although we are running at the moment 2 experiments at 2 synchrotrons, and I hope that our teams will survive without his support during that time. What we are doing actually, sorry, it doesn't. Excuse me, there is some technical problem. Okay, I can list now my presentation. So what we are doing now at synchrotrons, actually we use a diamond tunnel cell as a chemical reactor, which enables material synthesis at extreme pressure temperature conditions. And our purpose is to reveal both the crystal structure and the chemical composition of the products of chemical reactions at pressures exceeding 1 megabar. You may ask me why 1 megabar, why extremely high pressures are so important. The answer is very simple. A number of intriguing and very interesting phenomena have been reported at such high pressures. Phenomena including also room temperature superconductivity. But the problem is that this phenomena have not been attributed to a definite chemical compound with a definite crystal structure. For this reason, why it is so important? If there is no such an attribution, it is not possible to establish structure properties relationships, and this is actually crucial for understanding the nature, physical and chemical nature of the observed phenomena. Charged with the task to be able to review the crystal structure and the chemical composition, we have been working on application of single crystal X-ray diffraction at extreme conditions, taking into account that the products are very small and the mixtures are multi-grain and contain micro-sized samples, which we have to analyze in situ. I will tell you about our methodological and technical approaches and show you some results of our investigations. The first ideas in this direction probably originate from the time when we started super hot nanocrystalline and polycrystalline materials, including boron-doped diamonds. And that time, in the beginning of 2000, they were reported to be superconducting. And despite we confirmed the superconductivity, we couldn't find such a level of doping in individual diamond grains, which was necessary to explain the phenomenon. I believe that the answer of what superconducts in polycrystalline boron-doped diamonds is still, the question is still not answered, because nobody measured superconductivity on heavy doped single crystal diamonds. But this research was very inspiring because we found that the intergranular space in polycrystalline diamonds is filled by boron. And this turned our attention to the research on boron and boron allotropes and boron-rich compounds. In particular, in these experiments, we studied high pressure behavior of gamma boron, and you see single crystals of gamma boron loaded into the diamond anvil cell. The experiments were conducted at room temperature, and it was a very nice observation that the crystals could survive at pressures as high as 35 gigapascal. And this fact excited our imagination, and we thought that it would be very interesting to initiate a chemical reaction to irradiate the single crystal with laser and see what will happen in the result of this chemical reaction. The task is actually very challenging, and it is easy to understand why when we compare the size of our crystals in a diamond anvil cell with the diameter of the human hair. If we hit a crystal with laser, then we obtained a product of a chemical reaction with a grain size at the level of microns and at submicron level. So for this reason, we have been working on the developing of methodology, how to approach this problem during the last decade. And I'm happy that it is now well established. And our former PhD students and our postdoc spread the methodology all over the world, working in different institutions and at different synchrotron facilities. And last Monday, Stella Hariton, which is working now at Vitaly Prokopenko's beamline at the APS, gave a wonderful talk. And she explained all the details of the methodology, starting from the fundamentals and continuing with the description of the procedures which are applied at the APS. For this reason, I am lucky not to start from the very beginning. And I can also add that how we do this in Europe, in Hamburg, at the extreme conditions beamline at Petra 3 synchrotron. There we built single crystal diffractometer coupled with double-sided laser heating system. And you see the schematic how we realize the heating from both sides in the diamond anvil cell using so-called universal laser heads. But what is the difference in the procedure at the APS and in Hamburg? In Hamburg, at the APS, we can take a still image upon heating when the sample is not rotated in a diamond anvil cell. Still, X-ray diffraction pattern can be obtained upon heating. But in Hamburg, we placed these two universal heads, laser heads, on the common stage with on the goniometer where the diamond anvil cell is placed, and the whole system is rotated, and the system is rotated as a whole. So it means that we can not only irradiate the sample, but we can also rotate the sample upon irradiation and take what we call step scans and produce single crystal X-ray diffraction from the crystals from products of chemical reactions, which are now in a diamond anvil cell. The whole system is mounted on the general purpose experiment. You can see how the system looks like in reality at the extreme conditions line, how stable the heating is. And I would like to use this opportunity to thank the German Federal Ministry of Research and Education Foundation. And for the general users, the system is available since 2017. Now let's take a look at a real experiment in a diamond anvil cell when we heat a piece of iron placed into a diamond anvil cell along with oxygen. If in the beginning, the diffraction pattern looks like this, typical for polycrystalline materials, then after irradiation, we can see that it changes and we see fingerprints of the product of reactions which appear as very small grains or these grains may be grains of different phases. They may be differently oriented crystalline domains of the same phase, and each individual grains produces its own single crystal diffraction pattern. If we consider a single crystal or a single crystalline domain, then at each position, it produces diffraction spots on the two-dimensional detector. And upon rotation around omega axis, we obtained more and more diffraction reflections, which can be visualized in the reciprocal space, where they appear as arrows of points. And processing this data in the reciprocal space, we can determine unit cell parameters and prepare the data set for single crystal analysis for structure solution and structure refinement. Everything would be straightforward if we didn't have a mixture of all the crystalline domains of different phases, as I already told you. And the challenge is to separate the reflections which belong to the single crystalline domain and to eliminate the parasitic reflections which come from different sources. They can come from the pressure medium, from the gasket and diamonds themselves and so on. Unfortunately, the movie doesn't work. I will try to do something. Just a second. Switch off laser point. Yeah, now it works. So with using modern software, we use Crystallis for this purpose. We can visualize the reciprocal space using special additions to the program made by our colleagues, members of our teams. We can eliminate parasitic reflection, and you can see probably the straight rows of points here which belong to the same crystallite. And using software again, we can try to separate phases or domains. In this figure, they are shown by different colors. Each set of differently colored dots is a set which belongs to the same domain, and we can index the diffraction patterns separately and prepare the data set for separate data set for indexing, unit cell determination, and for the data integration. And after that, when we integrate the data set can be processed in other programs. Stella describes them very well in her talk on Monday. And after structure solution, we can come to the structure refinement. This is a demonstration of the results of our particular experiment when we studied chemical reaction between rhenium and carbon at very high pressures at about 2 megabar and 3000 degrees K. And using our methodology, our approach, and taking advantage of a very small beam size, which can be provided by ID11 at the ESRF, for example, we could make mapping of the whole pressure chamber and to see which phases are present in the pressure chamber, because the size of the X-ray beam is as small as this white square. And for each phase, we can determine the chemical composition and the crystal structure as shown in as shown here above of the map. Now let me please summarize in the retrospective the history of the development of in situ X-ray diffraction, starting from 1950s when all that began. I can say that in the middle of 60s, it was possible to get our first single crystal X-ray diffraction pattern. It was at very low pressures yet. In the middle of 1970s, it was possible to obtain first complete three-dimensional structure refinements, but during the next more than 35 years, the pressures were limited by about 15 gigapascal. And only with the efforts, due to the efforts of a few groups, including it was possible by 2010s to extend pressures up to dozens of gigapascal. But I would like to emphasize that all these experiments were conducted on single crystal, pre-synthesized and loaded into the diamond anvil cell. And only starting from about 2015, from the middle of 2010s, our group in Bayreuth worked out the procedure and methodology and developed the technique to that extent that it became possible to analyze products of chemical reactions in situ in a diamond anvil cell. And starting from the 2019, the pressures for such experiments were extended up to 2 megabar. Well, using this technology, we have studied a number of materials in different systems. We started from boron, as I told you already, from boron allotropes, boron rigid barytes, and studied silica and silicates, oxides and hydrides, carbonites, and Stella gave you some examples on Monday from the world of carbonites at extreme conditions. And I decided to give you some examples from nitrogen system and nitrogen transition metal systems for a couple of reasons. Actually, they are not well studied so far. If we compare the number of oxides and nitrides in the materials list in the ICSD database, you can see that the number of nitrides is much smaller, despite nitrides attract attention because of their perspective for electronics. And the other reason why nitrogen is so interesting, it is a very perspective material for high energy density materials, for producing high energy density materials. Well, now I would like to invite you to our high pressure chemistry kitchen, and our chief cooks on this kitchen and on all questions related to nitrogen are Dominique Laniel and Maxime Bykov, and they are first authors of the papers I will be presenting now. Nitrogen, let me start with a very simple recipe. When we put only nitrogen into a diamond anvil cell and see what will happen. Dozens of years of investigations at extreme conditions, at high pressures, allowed formulating some empirical principles regarding the behavior of elemental materials at high pressures. In particular, one of these rules says that elements behave at high pressure like the elements below them in the periodic table at low pressure. And it holds for the Prictogens family of elements quite well. If we consider elements up to phosphorus, for example, phosphorus adopts the structure of alpha arsenicum at pressures higher than arsenicum itself. But when it comes to nitrogen, it seems that for nitrogen, the rule doesn't hold. Because what would we expect for polymeric nitrogen at high pressures? we would expect that it will adopt the structure of black phosphorus and the structure of alpha arsenicum. And it is supported by theoretical calculations, which started as early as in 1980s. And but realized was the structure of so-called cubic wash nitrogen. And you can see here how the structure looks like, and it was synthesized at pressures of 110 gigapascal. In 10 years since that time, there was another report when so-called LPN nitrogen allotrope was reported. And this phase caused some questions. First question was that calculated and experimental volumes didn't match. And with the report of one more nitrogen allotrope, one more question arose. It turned that the lower pressure LPN phase appears to be denser than the high pressure HLPN phase. I would like to say that the structure interpretation for LPN relied on calculations because only powder X-ray diffraction was available, and it was not sufficient for the structure interpretation of the new allotrope. So all the inconsistencies which arrived had to be resolved, and we put nitrogen into a diamond anvil cell. You see how the cell contracts when the nitrogen is pressurized. And after laser heating, we obtained a material which was analyzed using the technology which I have introduced to you. And we know that this material is other structural to black phosphorus. Wonderful. But what to do with the LPN? And the answer came from Raman spectroscopy. When we consider the Raman spectrum of black phosphorus and those reported for LPN, they appear to be identical. It means that the phase is the same. It gives the same fingerprint. Now the question is which structure interpretation is correct, and we conducted simulation. We calculated Raman spectrum of black phosphorus nitrogen, and we obtained 8 modes in total. And our experimental spectrum resembled all the minor details in the theoretical spectrum. But when we calculated the Raman spectrum for nitrogen with LPN structure, it gave us 45 modes, and the spectrum has nothing common with that produced by the material. So the conclusion was clear. The interpretation based on theoretical calculations and powder X-ray diffraction was incorrect. And with establishing nitrogen with black phosphorus structure, all inconsistencies regarding volumes mismatch and the sequence of phases were resolved. So it looks like it is a happy end. Nitrogen, which was a black sheep in the Prictogens family of elements, is now reunited with the Prictogens family, and this happy end was very exciting. And Martin Polikov produced a film on this story. which got more than 400,000 views on YouTube, that made this paper the most popular of whatever papers we have ever published. Well, let me see, you will tell me that the recipe was very simple and that the order on the nitrogen kitchen was easily established, but I will show you what happens when we start to complicate the recipe and add transition metals to nitrogen. The results are not only astonishing, they are absolutely unexpected. And before I will show you these results, I would like to say a couple of words why pressure is so necessary when we are dealing with the synthesis of binary nitrides. Our purpose was to synthesize binary nitrides featuring polynitrogen species. It is for this reason. It seems that the synthetic route is very simple. One could put a metal together with the gaseous nitrogen, heat all that, and directly obtain the nitride which is desired. But everything is not so simple because of the nitrogen triple bond is extremely strong. And to break this bond, the system has to be heated to very high temperatures. That makes the nitrides unstable at such conditions if we consider simple thermodynamic relationships. So, how to suppress this decomposition? The answer is apply pressure. What was done, and actually the first pentazolates, salts of alkali metals featuring 5-member nitrogen rings were synthesized at high pressures. It may be considered not so practical, the synthesis at high pressures, but if a material would show some useful properties, then the chemists are very smart. They will find a way how to synthesize the material at ambient pressure, and it was shown on example of pentazolates, and it is a very important moment because high pressure synthesis shows a principal possibility to synthesize some particular materials, and then chemists work on a possibility to synthesize it, stabilize the materials at low pressures. Pentazolates contains, as I said, some contains 5-member nitrogen rings, and the first binary material, binary nitrides, which features polymeric nitrogen chains, was synthesized also at high pressure and by our group. And you can see that the structure of iron tetranitride features polinitrogen zigzag chains running along the C direction. What is the beauty of single crystal X-ray diffraction? It gives us chemical composition, it gives us a unit cell parameter, space group, and interatomic distances, which we can determine because single crystal X-ray diffraction provide us with the atomic coordinates. Based on the analysis of interatomic distances, we can come to conclusion about a bonding scheme in such materials, what we did. And our proposal was supported by theoretical calculations. And what is also important, that first work we conducted at pressures of 135 GPa, but another experiments were realized at much higher pressures, at 180 gigapascal, at ID11 at ESRF, which provides a very small size X-ray beam. And you see, due to these technical capabilities, we were able to refine the structure at such extreme pressures with the quality of the refinement not less and even better than the quality of the refinement at much lower pressures. And the results of experiments at high and lower pressures match very well. Well, these experiments inspired us for further investigations. And when we added another transition metals to the nitrogen system, we obtained not only absolutely unexpected results, we obtained counterintuitive results, because when we talk about pressures as high as 1 megabar, one can imagine that all materials try to contract and the atoms should, according to our intuition, to pack tightly, should pack tightly in the given volume. But it turned to be not the case, because in this experiment, we observed so-called metal-inorganic frameworks, the material featuring structures containing channels and pores and channels. They are filled by nitrogen molecules, and for this reason, they are not only metal-inorganic frameworks, they are inclusion compounds. Our results on hafnium, tungsten, osmium were published in Angewandte Chemie. We have publications on other transition metals, rhenium, for example. Let me now to introduce you the structure more closely. The structure which is characteristic for tungsten and rhenium nitrides looks like this. It can be interpreted as a metal-inorganic framework built of the layers of nitrogen and metal atoms, and these polynitrogen chains serve as the linkers for nitrogen or for metallic atoms. The analysis of the analysis of interatomic distances supported by theoretical calculations allowed us to propose such a type of the bonding scheme. And we found that actually polydiazodenyl chains in this compound act as classical ligands, acting as donors, acting as donors for nitrogen metal bonding. And the sp2 hybridization of nitrogen atoms themselves imposes a metal to be in the same place as the coordination nitrogen chain. For this reason, the restrictions on the geometry of the system caused by the polar covalent character of metal-nitrogen bonds is the first stabilizing factor of this interesting metal-inorganic frameworks. Now, what is clear for us intuitively is that another factor is the inclusion of nitrogen molecules into the pores. They stabilize the structure, and such a simple and intuitive conclusion was confirmed by our calculations. We found that if nitrogen molecules are removed from the pores, then the structure collapses at pressures above 35 gigapascal. Let us look at another metal inorganic framework at pressures about 1 megabar. This is the structure of osmium nitride. It is also an inclusion compound. Now we see that there are two types of channels in the structure, and they have different shape. And in this structure, we have already two types of nitrogen linkers for osmium atoms. This double bonded nitrogen groups and the polynitrogen chains which we have already observed in tungsten and rhenium nitrides. When I look at this structure, I'm always fascinated because they are beautiful, just aesthetically very beautiful, and their diversity is striking. And this is the structure which we found for gadolinium nitride. One more linker added into this company, and I won't analyze this structure in detail. We have no time, but I would like to attract your attention to the fact that in the same pressure chamber, as the same pressure temperature conditions seemingly, we can observe numerous phases. And it is certainly because the fact which was emphasized by Robert Hoffman 2 weeks ago in his talk, that we are always dealing here with non-equilibrium conditions. And for this reason, different phases can be synthesized and with different structure, even if they have the same brutal chemical formula, like in the case which I will demonstrate you now. This inclusion compound has the formula HF2N11, and the material which was found in the same pressure cell has the same chemical formula, but it has absolutely different structure. It is not an inclusion material anymore. The type of polynitrogen chains is also different. Such chains we observed in nitrogen tetranite or in iron tetranitride. We see two types of linkers here. These are dumbbells of nitrogen atoms, and these are separated nitrogen atoms. And these chains are running along the C direction. They are shown here in this blue color. But what is exciting in this material or in this structure is that it features double helix constructions, which are very unusual for inorganic materials. They run along the C direction perpendicular to the screen. Well, I have to stop with this example now, and just again to emphasize that in non-equilibrium conditions, when there are many phases formed at the same time. Using our approach and single crystal X-ray diffraction at such extreme conditions and the capabilities which are provided by modern synchrotron facilities, we can determine chemical composition and crystal structure of the product of complex chemical reactions at extreme conditions. If now we will put all known nitrogen polyanions and polymeric nitrogen forms on the time scale, which starts from the late 19th century, we can see that the number of these polyions and polymeric forms, which was revealed due to high pressure X-ray diffraction, and especially high pressure single crystal X-ray diffraction, is much larger than the number of these forms and polyions known for about 100 years before. Now I would like to show you a couple of examples from the world of hydrides, for which extremely high up to room temperature, superconducting temperatures were reported. And it is not the purpose of my talk analyze of many works which have been published since the first claim of very high superconducting temperature in the sulfur hydride system. But the problem of many works done in this direction is that the materials or chemical compounds are not identified in these experiments. And starting from the very first publication, I would allow to cite from this paper, where the authors wrote, however, the particular compound responsible for the high TC is not obvious. This situation still holds. There are many mismatches in the reported temperature determined by different methods. And there is a discrepancy between the theoretical predictions and between the theoretical predictions and experimental observations. So once again, in most of the works, the chemical composition of the compounds to which the phenomena are attributed are not known. I would like to give you just one example of our investigation of the sulfur hydrogen system at extreme conditions, and we'll show you which phases we obtained in our experiments. In our experiments, we found sulfur hydrides, which were probably were very difficult to predict, because in tetragonal phase we found there are 100 sulfur atoms in a huge unit cell, and in another hexagonal phase there are 112 sulfur atoms. And we solved the structures using single crystal X-ray diffraction. In the first case, it was 62 GPa, and in the second case, it was 150 GPa. These phases were hidden in the pressure chamber. They could not be detected using powder X-ray diffraction. Because you see that the powder diffraction data, the powder diffraction patterns, which we obtained from the same sample, which featured the newly synthesized sulfur hydride with 112 atoms in the unit cell, was not seen actually in this diffraction pattern. Only those reflections which are marked by asterisk, only 4 reflections could be observed. And while single crystal X-ray diffraction gives us a very rich and distinctive diffraction pattern, which can be analyzed and the structure can be solved. So the diffraction patterns are, powder diffraction pattern is dominated by high symmetry phases, which have been seen before. And we also observed these phases in our experiment, both tetragonal and cubic phases, and we refined atomic coordinates for these phases in our experiments. But the major conclusion is that these phases could not be observed and could not be predicted so easily, as you see. Now the question is how much hydrogen is incorporated in the structures. And here, single crystal X-ray diffraction couldn't help us. We had to apply to theoreticians and make theoretical calculations. We calculated the dependence of the unit cell volume on the number of atoms per 140 sulfur atoms in the first case and 112 sulfur atoms in the second case. And using our experimentally determined volumes, we could estimate the content of hydrogen in our sulfur hydrogen compounds. And you see now the result which theory helped us to obtain. And in these structures, you see now the positions of hydrogen atoms. It is one of many possible variants because theoreticians suggest that the materials are non-stoichiometric, and in the particular cases of these two structures, they have such chemical formulas. And it is still, I would like to admit, it is not so easy to locate hydrogen in the crystal structures using single crystal X-ray diffraction. So we think about the possibilities to visualize, to localize hydrogen atom in the enigmatic and interesting structures which can be revealed at extreme conditions. And we think that a very prospective direction is the development of high pressure solid state nuclear magnetic resonance. And the major player in our team on this field is Thomas Meyer. And it is not the topic. It is not the topic of my talk today, but I would like just to let you know that we made some progress in this direction, improving resolution of solid state magnetic resonance in dense molecular hydrogen, and also in the direction enabling experiments not only at high pressures, but at high temperatures at the moment. And now we can conduct experiments, solid state NMR experiments at pressures up to 200 gigapascal and at much at moderate pressures at the level of 25 gigapascal at high temperatures of about 1000 degrees K. So first results have been published on metallic hydrides and on the behavior of the dense molecular hydrogen. And it is just for your information. And our group is very open. We are very happy to share the methods we have developed. And there was an international summer school in Bayreuth last summer on novel methods of atomic and electronic structure studies at high pressures. It was a great success. And we hope that this summer there will be another summer school. So those who are interested to learn how we conduct our experiments, to learn our approach, both in single crystal X-ray diffraction on multi-grain, multi-phase samples and on solid state nuclear magnetic resonance, you are welcome. You can see, you can look at our webpage, the programs, there will be announcement there. And now I'm concluding my talk, and I would like to thank all the major contributors to the research I have presented you. And there are many more people who contributed with their ideas, with their technical skills to this research. And I'm very, very grateful to all of them. And I thank you for your attention. And I'm ready to answer your questions.
Thank you very much, Natalia. Wonderful talk. Great to see this review as well as all the new data and introduction of new techniques. It's also nice that it was paired with Stella's talk on Monday. So
yeah, absolutely.
We'll try to do that more often. I'm sure there are questions from the audience for Natalia. Just unmute yourself or put the question in the chat box. Maybe I'll start. The work on nitrogen is very nice. One question is, focusing on the black phosphorus structure, actually McMahon and Lassar discussed this in a PRL they published in 1985, but no one seems to be citing that paper. That was the first prediction of monatomic nitrogen at high pressure. Are you aware of that paper? You are muted, Natalia. Comments, questions?
Can't hear her.
Natalia?
Yeah.
You're unmuted now. Okay.
Have you heard anything?
No.
No, I'm sorry. Some technical problem appeared. So there was no, I didn't pretend to cite all papers in the, paper, but I believe that it was on the slide which I showed with regard to this work. Are you satisfied, Russell?
I didn't see it, but it's okay. It reminds me of the Vigner and Huntington paper on metallic hydrogen, when in the last paragraph, they talk about all the other phases that should be stable, the layered structures that should be stable prior to the full dissociation to produce the symmetric structure, but no one seems to pay attention to that final paragraph of that paper.
Okay, that's the life.
Just a comment.
Thank you, Russell.
So this is rolled here. It's beautiful material and fantastic to see those superimposed single crystal patterns and being able to take them apart. And the nitrogen structures are astounding, quite incredible. I just wanted to mention that that we had done some calculations in which we predicted the polyacetylene chains of nitrogen. Ours were on LiN3, lithium azide, the calculations in 2013. And Dasari Prasad, who is now at IIT Kanpur, did those calculations. I just want to mention two other patterns of nitrogen which emerged in those calculations. One was ones where nitrogen, where the metal atoms completed a 6-membered ring with 5 nitrogens, not a 5-membered ring like you have with 4 nitrogens. And the other thing was the hexagonal N6, which came out in our calculations at certain pressures, but which has not been predicted, which had not been seen otherwise. Anyway, making these things is much more important than doing the calculations. So that's beautiful work.
Thank you, Roald.
More questions? Well, thank you very much, Natalia. It was a wonderful talk again, and we look forward to hearing from you all in the future. And hopefully we'll be able to travel once again and interact like we used to. So thank you.
Exactly. Thank you very much. Bye.
It was beautiful.